this onto Moodle after the presentation today. All right. Yeah, great. Let's see. Can you just help me out here? Can you try and can you raise your hands, or as like there's a button to communicate, right? I see a hand. Great. Thanks, guys. So my plan here today, I have a few slides. I'm just going to introduce the material. You know, this format, it doesn't let a lot of the kind of back and forth conversation that we have in classroom. It kind of doesn't allow for that as easily. But if there's something that it just isn't clear as we go, you can just pop your hand up like that. I have it on the side here so I can see. And then we can just stop and ask a question. Oftentimes, you know, I forget what it's like to learn this for the first time. And sometimes, you know, your understanding of these concepts can just hinge on like a simple, like a, you know, a definition of a term, or, you know, whatever that I'm just using that you just don't understand. Like Martin said, I'm a mechanical engineer. I'm a postdoc in Martin's group. I've been here at ETH since 2018. I graduated with my PhD in 2015 in mechanical engineering from the University of Minnesota. So a lot of these terms, like, you know, even notation between mechanical engineering and geoscience, right? We often will use different symbols to mean the same thing. So I kind of have this mechanical engineering sort of palette of symbols for, you know, density or whatever that I'm used to, and that may be new to you. So just raise your hand and I can clarify that. All right. So there's two classes. Today we're going to talk about hydrothermal power generation. So this is making electricity with geothermal sources. Next Friday we're going to do CO2 geothermal. So what happens when you have CO2 in the ground instead of water, and you make power with CO2? And that's sort of a specialty of our geothermal group, which is really interesting, but that'll be next Friday. Today I'm going to cover some basic concepts like heat engine, making electricity from heat, generating power, thermal efficiency, and the circulation mass flow rate of a geothermal fluid, and some pumping. So this is going to be a very pragmatic approach where I just give you some equations and a little bit of background. And then there's some homework for you to do at home where you can actually apply these. It's pretty simple, but if you just do the work, you shouldn't have any problems on the exam. So last year, my lecture, I think, was a little too conceptual and people had problems in the exam. So this year, I just wanted to say up front what exactly my expectations of you are as a student, and the types of questions that I think you should be able to answer after you do the exam. So, you know, for the presentation today, I'm going to cover all these topics, but I expect you to be able to calculate a Carnot thermal efficiency, or real thermal efficiency, a thermal efficiency with actual numbers of power and heat, a circulation mass flow rate, pump power, and finally the geothermal electricity generated. And this, it might be a little unclear now, but it should be clear at the end of the lecture. It should be even clearer after you look at the homework problems. There's a textbook as well. DPIPO has a geothermal energy textbook that covers all this, and so I'm covering chapter 8 in the DPIPO textbook. So basically, how to make electricity. You can use heat. Martin says it a lot. If you have a use for the geothermal heat, like district heating in greenhouses or whatever, that's great. But usually you need to make electricity with a geothermal source, because electricity, there's a market for it. You can sell it anywhere. You know, you can run your power lines long distances to send your electricity elsewhere. So in geothermal energy, we produce heat from the earth somehow, and we have to make electricity from it. You make electricity using this thing called a heat engine. I'm gonna turn on my, using a heat engine. A heat engine is just something that it takes thermal heat from something that's hot, say the earth, right? And it transfers that heat to something that's cold, say the air at the surface. So by transferring heat from something that's hot to something that's cold, you can just make electricity doing it. It's a thermodynamic concept. That's just as simple as that. Just by moving any heat from something that's hotter to something that's colder, you can always make electricity. So theoretically, you can move heat from someone's body at 40 degrees or 37 degrees, right? From someone's body to the atmospheric air at 10 degrees or whatever it is outside, and you can make electricity with that heat that you move. Now, it's the efficiency at doing that, the efficiency by which you can convert this heat to electricity is very low, so I know one does it, but you could theoretically do it. This concept is used in renewable energies and fossil energy. So for instance, here we have a solar collector, central solar power generator, and you have all these mirrors basically that reflect sunlight to a central place, and this thing gets very hot, so that hot thing then generates electricity. Here's another schematic of that same system. This receiver gets really hot. The same thing in a nuclear plant. You have some nuclear reaction that makes water really hot. And then you use that hot water to drive a power cycle and make electricity. In a coal plant, you burn coal to get something really hot and to make a power cycle, to drive a power cycle. So all these you can see here, there's this loop here. This is the water loop. It has a turbine and a boiler and a pump. And the same thing over here, you have a turbine and a boiler. You have this little closed loop that is the Rankine cycle, and that's the thing that generates electricity. That's the heat engine. All right, so this heat engine in geothermal energy, right? I always seem to need to mention this, but people seem to forget that just the earth is hot, and something that's hot can make electricity. So you can you can transfer heat from within the crust where it's hotter to up on the surface. Just on average, the Earth's crust increases in temperature as you go down by about 30 C per kilometer. And an average surface temperature for North America and Europe here is about 15 degrees C. And those are just kind of standard numbers that are used often in calculations for power. So just things to remember going forward. Now the traditional geothermal energy takes place along the edges usually of tectonic plates like this. Doesn't have to, but these are hotspots that are usually located along there. For example, in California, there's the largest geothermal development in the world is on the left, on the west coast in California. And that's because you have the tectonic plates. It's basically fractures in the Earth's crust, right? And these fractures let the hot water just buoyantly rise up to the surface. And so these are suitable for geothermal just because you don't have to drill as deep. So instead of this 30 C per kilometer, which is the temperature gradient in most, just in non-fractured areas where you just need to drill down through the crust, when you have fractures in the crust, you can basically get the hot water at the surface. And then it's maybe 300 C per kilometer is the temperature gradient, right? So that's where most geothermal has been traditionally developed. In developed countries, that's mostly all been developed already. So we're just focused on geothermal energy with just standard temperature gradients of 30 C per kilometer. And that's what I'm going to focus on today. So a geothermal power plant, this is looks something like this. This is an example for an EGS system, which is in basement rock, but it looks very similar for something shallower as well. Basically, you have a reservoir that's down deep that has hot rock, right? And you circulate cold water. You circulate cold water down into this formation. It gets hot. You produce the hot water back up to the surface through your production well, and then you run it into some sort of power cycle at the surface. So in here they have a heat exchanger. So on this side you have the geofluid. Hot geofluid gives off its heat to a second fluid here. In this, we call it the secondary loop, which has a turbine and cooling towers and everything within it. So this up here is what makes the electricity. So I replaced that at the surface with just a box. This here I have just as a power cycle now. This is what makes electricity that you send, you sell to the grid. The wells here I've replaced just with this cartoon, these green lines that simulate the injection and production well, and down here at depth we have just a reservoir. And in the geothermal plant I'm talking about today, it's a closed loop. So whatever water you inject down here, you run it through a reservoir and then you produce that same water out. Obviously in reality that's not the case and you have losses, but we'll start with this simplified example. And then you have a pump in your production well that pumps the fluid to circulate it. So there's two ways you can calculate the geothermal power. The geothermal power that you sell to the grid, that's this W net here. It's the power that you generate from this power cycle, from your heat engine, minus the power that it takes to pump and circulate the fluid, right? So you can make 3 megawatts of power here. It takes you 1 megawatt of power to circulate the fluid, so then you can sell 2 megawatts to the grid, right? So you can calculate this by actually calculating these powers, the pump power and the power from the power cycle. Or you can use this approximation using something called the thermal efficiency. So the power that you sell to the grid is the thermal efficiency times the heat that you produce from the reservoir. This heat produced, is the mass flow rate times the specific heat of water, which is just a constant, right? Times the temperature difference that's going into your power cycle and whatever is coming out. So this is just your kilowatts. Usually we use kilowatt thermal because this is thermal heat. The power that's generated, this is kilowatts electric. Because it's high grade energy, it's electricity. And the thermal efficiency is your conversion efficiency between the low grade heat that you produce, the thermal heat, and the high grade electricity. So we're going to use this approximation using the thermal efficiency to start, just because it's an easy place to start and gets the concepts across. Okay, so first of all, to calculate the electricity, then we need to know what this thermal efficiency value is to start. All right, thermal efficiency is the power generation divided of the whole plant divided by the heat input into the plant. So it's like, if this is all the heat that you put in, this is the electricity you get out. This tells you, it's an easy metric to see. It tells you how, how much heat you have to throw away. So if this, in this example here, right, you can have 10 megawatts of heat input into the plant. The heat output is 9 megawatts. And then the power that you generate, the electricity you generate, is 1 megawatt, just because this has to be true for a power cycle. The power that you generate has to be equal to the heat in minus the heat out. This is just the first law. It's the first law of thermodynamics. Use a power cycle cartoon again. So for example, this plant here, this is a geothermal power plant in Hawaii. There's the wells that are located remotely that provide the heat input into this power plant. This thing sends electricity to the grid, and then there's heat that has to be rejected just because you can't turn all of this heat input into electricity because of the conversion efficiency. So you have to reject some to the atmosphere. And they do that. This is low temperature heat, 30 degrees or something like that, that is blown out through fans and rejected to the atmosphere. In this example, if this power generated is 1 megawatt, that's 1 megawatt divided by 10 megawatts. Your thermal efficiency in this case is 10%, which isn't unusual for a geothermal plant. There's many ways to calculate the thermal efficiency. There's the Carnot efficiency and the triangle Carnot efficiency. These are both like theoretical maximums that nature limits you, that physics limit you to do. There's a rule of thumb, different rule of thumbs like 20% of Carnot, and there's empirical correlations from literature. And the last thing you can do to calculate thermal efficiency is, of course, simulate the actual power cycle. You can simulate a Rankine cycle. You can simulate the geofluid pumping and figure out what the actual thermal efficiency is. It gets harder to do these things as I kind of go down here, but it becomes more accurate, right? So I'm going to talk about each of these now. So there's these two fundamental thermodynamic cycles. This is from the DiPeppo textbook, chapter 8. These are derived from fundamental thermodynamics. It's just the laws of nature working against you here. The Carnot cycle is the maximum, the greatest thermal efficiency that can be calculated between any two temperatures, between something hot and something cold. That's the Carnot thermal efficiency. There's something called the triangle cycle, which DiPeppo talks about too, which is more closely estimates the power generation of an actual cycle that's with the same two temperatures, the hot temperature and the cold temperature. So both of these can be used to estimate the thermal efficiency, or at least give you what the maximum possible thermal efficiency is. So you have to use temperatures in Kelvin to do this, right? You get a different answer here if you use Celsius, and this was an exam problem last year, right? And people messed this up. Obviously, if you use a low temperature that's negative, this value would be greater than 1, and you can't have a thermal efficiency that's greater than 1. You can't make energy, right? So you can't use Celsius in this equation. You have to use Kelvin. So these two will tell you what sort of the maximum thermal efficiencies that you can get in a power cycle. Non-theoretical thermal efficiencies. So you can take that Carnot value, which is the maximum, and just say, tends to be true approximately, is that you can get about 20% of that is what the electricity you can actually convert from heat. So you can convert about 20% of Carnot is what you can make from heat. And so this is just it's a simple way to acknowledge that you can't make, the Carnot efficiency is theoretical and you'll never get that, but you might be able to get 20% of that. Also, Zaruk and Moon, they have a literature review they did of geothermal power plants a few years back, and they just found this relationship for geothermal power plants. So if you have the high temperature and the low temperature, you can just calculate what the thermal efficiency is going to be. And these are better for calculating thermal efficiency. The last thing you can do is you can actually simulate a power cycle at the surface and calculate it, right? It's a little backwards because if you're simulating a power cycle, you don't need the thermal efficiency. You can just actually calculate the power. But, just for the sake, for giving you all the full range of options here, I'm just showing this as well. I don't expect you to be able to make a power cycle like this. but I'm just showing you as an example. So this is for R245FA, which is it's a refrigerant that's sometimes used inside of power cycles to make electricity. You know, you can use water, you can use ammonia, you can use isobutane, a whole bunch of different things. This is a TS diagram showing the different state points within the power cycle. This one was just from a paper that I'm working on right now. But basically, you have a pump, you preheat the water, or the R245 gets preheated by the water you produce from the ground, from the geofluid, and you boil it, you run it through a turbine, you have to cool it, and then you reject the heat at a low temperature back to the atmosphere. So you could calculate the thermal efficiency with this cycle too, the heat, or the power generated divided by the heat input. So the power generated is the power that you make from the turbine minus this little pump, the power that it takes to circulate the fluid in here. So that's the top part of the fraction here. And the heat input is the heat that it takes in the preheater plus the heat in the boiler. So these two on the bottom, and then you can calculate the thermal efficiency of this guy is about 8%. So, you know, this thermal efficiency is a gross because it doesn't take into account the power to run the geofluid pump, but this is still kind of lets you know the sort of values of thermal efficiency we're talking about here. So this is for 100 Celsius reservoir, 100 Celsius temperature water you're bringing out of the ground, about 8%, you know, you could expect to convert to electricity. All right, so we talked about mass thermal efficiency. The next thing you need to know to calculate the geothermal heat for this cycle is the mass flow rate that gets circulated, the geofluid mass flow rate that's circulated here. So we're going to talk about that now. All right, so for this analysis, we're going to assume the geothermal system is closed. This, like I said before, the geofluid that's pumped into the reservoir is the same that comes out, and the mass flow rate is the same everywhere of this geofluid. And this is down here in the reservoir, and this is up here at the surface. A pump generates a pressure difference which drives and circulates the flow. That's what causes fluid to circulate. And that's just to overcome losses when you move flow, either through piping up here or through a reservoir. It incurs losses, irreversible losses that just have to happen to move the flow. So the losses in all of the pipe and in the reservoir have to be equal to whatever pressure increase is caused by the pump. So this pump pressure increase is equal to the pressure losses in the pipe and the reservoir. This pump pressure increase, usually this is an optimization, but as a first approximation, you can just say it's 10 megapascal, which is just because 10 megapascal is the biggest pump that you can buy that can be downhole in a well like this. So you can have bigger pumps at the surface, but these pumps have to be down below the surface. And we'll talk about that later. But the maximum, more or less, that you can do here is about 10 megapascal. The pipe losses, this is a Darcy-Weisbach equation. The pipe losses are equal to the friction factor, which is just assumed 0.02 for you. The length of whatever pipe you pump it through divided by the diameter of the pipe to the 5th power. 8 over pi squared. This is the mass flow rate squared, and divided by the density of the fluid you're pumping, in this case just water. And in the reservoir, the pressure losses are calculated using the Darcy equation. The Darcy, it's different because it's laminar flow within a sedimentary reservoir. So we use the Darcy equation, and in this case, the pressure losses are proportional to the mass flow rate to the 1st power. This is the viscosity of the fluid in the reservoir divided by the density. This is the permeability of the reservoir, the thickness, the length of the reservoir that you're piping it through between the 2 wells, and the diameter of your wells. So this is an analytical solution that's just derived from a 5-spot well pattern where you have 4 production wells on a corner. This is a 5-spot is a standard sort of well pattern and spacing that we use to calculate, to calculate heat extraction from a geothermal reservoir and for pressure difference calculations. And there's a central injection well and then 4 production wells on the corner. So this is the loss between the injection and the production well in this case. If you use a different reservoir with a different pipe configuration, you would have a different solution to this Darcy equation here. All right, so we have 3 equations here. Our 3 equations, right? This is 10 megapascal, so you can just solve this. I solve this for these reservoir parameters here, so a pipe diameter of 10 centimeters, a well depth of 2.5 kilometers, so the total pipe length is 5 kilometers. In the reservoir, I used 50 millidarcy permeability, 100 meter thickness, and 700 meter spacing. So when you plot the pressure, the sum of these two is d pipe total. So when you plot this versus mass flow rate, it's a second order curve here, right? Because you have the mass flow rate squared. So this is the pressure difference total. The blue line is the pressure difference only from the pipe. So the difference between these two is then the pressure difference from the reservoir. I told you before the maximum pressure that you can impose on the system is about 10 megapascals. So I've just drawn a line at 10 megapascal here. And then the mass flow rate, where it intersects the total pressure difference, that is the mass flow rate that the system is going to operate at. So in this case, it's about 16 kilograms per second. I did it over here as well. This is for a more permeable reservoir, 500 millidarcy reservoir. In this case, the flow rate is about 32 kilograms per second. So this is just something that I did in Excel to see how these curves looked. You could also, if I guess you were bored, you could also just solve the system of equations by hand. So this is the pipe loss equation, which is mass flow rate, a product with mass flow rate squared. This is the Darcy equation, which varies by mass flow rate, and then the pump is a constant. This is just a quadratic equation. This is A, this is B, this is C, right? And then the mass flow rate that the system would operate at is a result of this, is solved here. And I would guess that one of these mass flow rates is going to be negative. I've never actually solved it this way. I just use Excel, right? Anyhow, so this is how you calculate the mass flow rate of the system. So that was mass flow rate, the mass flow rate term. This is a constant. The last thing you need then to calculate the geothermal power, is the temperature difference between the temperature going into the plant and the temperature coming out. So, right, and this is all for a hypothetical. The goal here is to calculate the power, the geothermal power, for a hypothetical plant, right? So like if I said, hey, you have a geothermal reservoir that's 100 C, over here, and it's 2.5 kilometers down, what power do you expect this plant to generate, right? This is a quick way you could just calculate that. Obviously, if you actually had a working plant, you could just, use the actual values of heat going into your plant and heat coming out. But because we're just doing this first estimation, right, you have to guess at what these values are going to be, and it changes the power generated. If you guess a different power output here, right, everything else constant. If T out is different, it's going to change the power that you generate. So we need to think about this a little bit. So what temperatures do we use here? This is just the power cycle. There's the temperature going into it and a temperature coming out. First, the temperature in. That's kind of the easy part. This we can just assume it's the same as the temperature of the water in the reservoir. There's going to be temperature losses as the water comes up the well to the surface because the surroundings around the well are colder, so it's going to lose heat. It's going to lose heat in the pipes at the surface, but usually not that much. Water has a high specific heat. It's able to hang on to that heat pretty well. So we can assume it's just equal to the reservoir temperature. The reservoir temperature for a non-fractured reservoir, it's the temperature gradient. This is that 30 C per kilometer, right? Times the depth of the reservoir, plus the average surface temperature. So if we have a 3 kilometer deep reservoir and a 30 C per kilometer gradient and a surface temperature of 15 C, we can expect the reservoir temperature to be about 105 Celsius. So that's a good estimation. Now for the output temperature. So ideally, we like the output temperature to be equal to the air temperature, right? That basically means that, we've taken all of the heat out that we possibly could. If, this is the reservoir temperature, this is the air temperature, it means we've taken all the heat out, we've used it all to convert to electricity, and that's great. It means we aren't wasting anything. But just that doesn't happen in reality. And I'll explain that to you with this guy here on the right. This is from DiPeppo in from the textbook. This is something called a TQ diagram because you have temperature on the Y and heat transfer, or Q, on the X here. This represents the heat transfer between the geofluid and the fluid inside of the power cycle. This is the heat transfer that happens in the preheater. In the preheater, the temperature of the second fluid increases, so R245 or isobutane or ammonia or whatever. And then in the evaporator, the heat inside that second power cycle vaporizes. That's in the evaporator, and that happens at constant temperature. When you boil water, right, it's a constant temperature process while you inject heat into the system. And this is this curve up here is the brine or the geofluid that you've produced. This is how its temperature varies, and it's just it comes out of the ground here at the temperature, the T in, or the T reservoir temperature. And it just decreases linearly as heat is removed. The temperature of the geofluid decreases to the output temperature. And the slope of this line, is constant if you assume a constant specific heat, which is more or less true for water. So it's something like 1 over the specific heat is the slope of this line. So ideally what you want, right, is you want the output temperature, the temperature of fluid coming out of your power cycle at the surface. You want that output temperature to be as low as possible because that means you've used all the heat. So we'd like it to be this ambient temperature. But there's a different consideration that something else we have to take into account here, and that's just the dynamics of what's going on inside of our power cycle. The secondary loop that's inside of our power cycle has some dynamics, and that's just this preheater and the evaporator, because they're two different processes. One's a constant temperature process, and the other one, the temperature is changing, right? And this represents the temperature difference at any point in the heat exchangers. At any point in the preheater as you move along, and in the evaporator when you move along here. If you want heat to go from your hot geofluid to the fluid inside of the power cycle, this needs to be hotter than the temperature inside the power cycle, right? You can't transfer heat from something that's colder to something that's hotter. Heat just doesn't go that way. So the temperature needs to be always greater than the power cycle. So you can't have, in this case, this ideal line. You can't have this because here the temperature of the geofluid would be colder than the temperature inside of the power cycle. And then you couldn't transfer heat. You can't use 10-degree water to boil a geofluid at 20 degrees, right? It's going to take heat from the 20-degree thing. So the result is you have this so-called pinch point constraint, basically where you need to keep you need to keep the geofluid at least some fixed temperature difference greater than the secondary fluid. This is usually about 5 C or so, this pinch point temperature difference. So when you add this constraint, basically your ideal line is pushed up to here, and you're forced to have an output temperature that's greater than the ambient temperature. So this is the pinch point problem. You don't have to be able to calculate this or draw this diagram, but you need to understand why the temperature output is greater than ambient temperature. So then, okay, if it can't be the ambient temperature, what's another guess at this temperature output for this power cycle? Well, in work that I've done a lot, this is just a power cycle simulation with R245FA again. Just the temperature, the outlet temperature from the power cycle as a function of the inlet temperature, just for different inlet temperatures, tends to be about 60 C. Right, so you could say as a second option, you could just say, hey, I expect the output temperature to be 60 C. Right, that's another estimation or approximation that you could make that is justifiable. Of course, when the temperature coming out here is like 60 C, well, everyone's like, well, hey, you got 60 C temperature coming out of your power cycle. I mean, that's still hot, right? Why don't you make some heat with that? And so people get creative. They start adding second power cycles to the end here. They add another power cycle, but optimized to generate electricity at 60 C, which has a really low thermal efficiency, but it'll be something, right? And then you start running into trade-offs. That's called a bottoming cycle. And you start running into trade-offs between, okay, this has a really low thermal efficiency, and this power cycle, costs something to build the second bottoming cycle. So, is it worth it? So oftentimes we don't simulate that, and they tend to be kind of a break-even sort of thing. So a 60 C approximation is a good example. It just depends who is doing the calculation. Going back just a minute, these guys here, Zaruk and Moon, this T out is T ambient. They use this assumption and they did their analysis. It depends on, you have to think about the problem a little bit to know what to do. Okay, so that's two options for calculating the output temperature. All right, so we covered the temperature difference, mass flow rate, the thermal efficiency here. This is for the first approximation for estimating the pump power, or the geothermal plant power that we send to the grid. I'm going to talk briefly about this downhole pump. You can actually simulate this power cycle like the example power cycle I showed earlier. To calculate then the power that you send to the grid, it's the power from your power cycle here minus this pump power, right? So you could try and you could estimate the power to the grid using this method as well. So I'm going to talk about this pump power. This pump power, it's a pretty straightforward calculation. The pump power is just the mass flow rate divided by the efficiency of your pump times the integral of dP pump over the density of the fluid that it's pumping throughout the pump process. With water, we assume it's usually incompressible. So the density is more or less constant for water. So it just reduces to this. It's the pressure difference of the pump divided by the density of water. And this we just say is usually about 10 megapascal, right? So you can more or less calculate the pump power if you just know the mass flow rate of your system, which varies a lot. And the pump thermal efficiency is assumed to be about 90%. This is a good place to start, 80 or 90%. All right, this pump depth, I mentioned this before, but basically these pumps, the pump is often considered separately from the power cycle because these things have to be located in the field in the actual well. Whereas all this equipment here in the power cycle, this will be located centrally somewhere. and you bring all of the geofluid to it. This pump has to be located in the well because you have to place the pump in liquid water, which sometimes occurs at some depth, usually in the well that's not at the surface. You pump this water at depth with these downhole pumps. There's sort of two examples here of downhole pumps. This is from DPIPO again. Basically, you have a motor at the surface, you have your well, and then the pump is down here. It's a mechanical pump, and it's connected with just a metal shaft connects the motor to the downhole pump. And these things can be 0.5 kilometer to 1 kilometer deep. And this is the mechanical pump. On the right, we have an electric pump located down here in the well with an electric wire that goes up to the surface. There's kind of a trade-off between these two as well. These tend to be more expensive. Electric pumps tend to be more expensive because you have to replace them maybe every 2 years. It's pretty crazy how often they have to replace these because the electric motors, they're submerged in 150-degree water, and that just makes them burn out quicker. These line shaft pumps are what these are called. They tend to be more reliable, but I think you can't go as deep with these, like 0.5 kilometer only. But this is how you pump. You do geofluid pumping in wells. These pumps have to be located below the flash horizon, which is where the water turns to vapor. This is an example here where I explain this, the flash horizon. So basically, we start here with a column, a static water column. It means there's no movement of water within the well. This is the well. The blue is the water within the well. Down at the bottom here, I have 2.5 kilometers deep is the bottom of the well, and up here is at the surface. So in this example, I'm using 100 C degree water. 100 C degree water boils. The saturation pressure is about 1 bar, right? Atmospheric pressure, more or less. So if the pressure is below 1 bar for 100 C degree water, it's going to boil and become vapor. The pressure in this well varies by Bernoulli's equation, which is just it changes with the density times G times your change in height. So as you move up the well here, this is the pressure starting at 250 bar and going to 1. As you move up the well, the pressure is going to decrease until it's about 1 bar up here at the surface, right? And then, but the problem is once you start moving water, when the mass flow rate of water is non-zero, you have the second term, you have the frictional losses. The same thing we described earlier in the pipe, right? These pressure losses happen, which are a negative term. So pressure is removed from the system. So the pressure at the surface is going to decrease. If we look at this example, right, for the same downhole depth and pressure and temperature, because the fluid is moving now, the pressure is going to be 1 bar at some point below the surface. This is going to be the point where the water is going to boil. This is called the flash horizon, and this is something that a depth that you could solve for. Above this flash horizon, it's going to be all water vapor. And you don't want to pump water vapor, you always want to pump liquid. So you need to get the pump below the flash horizon, then you can pump it. So this just explains why you need to have downhole pumps and the depth you need to set those downhole pumps at. Obviously, every geothermal system is going to be different. But this is a good place to start. Let's see, this is just a pH diagram, might help you doing the homework. This is the pressure versus enthalpy of water. So at 100 C, right, the water, this is the phase change temperature for water. It's at 0.1 MPa or 1 bar. You know, for a higher temperature, you have higher saturation pressures. So this will help you calculate that. Okay, I've covered material from DePeppo. The citation that I've given you at the beginning of the slides here and also in the homework. I've made some homework problems that I'm posting on Moodle after class here. You should do them for next week. Again, just problems last year, right, with students on the exam were that they didn't even try to do any of these calculations until the exam. They just thought they could look at the slides. And just there's so much you learn by actually trying to do it and putting numbers on a piece of paper that it really helps you to do some actual applied work before the exam. I mean, part of my intention here, right, is that I've given you, I just covered these topics briefly here, but like you need to dig into the material to get a little better understanding of these different concepts that I've explained here. So the homework problems are going to be posted on the website after this, as well as the recording of this presentation and a PDF of these slides as well. All right. Well, that's all I have then. If anyone has any questions, I'd be glad to point out something in the slides that anyone has. Let's see here. Okay, doesn't look like anything. I'm going to stop the presentation, stop the recording now.